the really weird quantum world of electrons and the huge scale of our own planet, what if they could be connected by just one powerful idea?
It sounds pretty wild, doesn't it?
It does. And you sent us this fascinating analogy that really got us thinking. Tesla waves are standing waves the size of the Earth, like electrons are standing waves of their own size.
Yeah, it's a really provocative statement.
So that's our mission today. We're going to unpack that, like really deep dive into what a standing wave actually is.
Okay.
Then we'll explore how it shows up, at the tiny atomic scale and the massive planetary scale.
Right.
And then finally, we have to critically look at what Tesla waves even means. It's kind of slippery, isn't it?
It really is. There's a lot tangled up in that term.
Get ready for some, hopefully, aha moments. We're going to try and build a clear framework for waves and then really apply it rigorously to each bit of that analogy.
Sounds like a plan. It's a great starting point because standing wave sounds simple, but applying it across these totally different scales, well, it forces us to look at some really fundamental physics.
Okay, so let's start right at the beginning. What is a standing wave? Why does it stand?
Okay, well, basically, a standing wave, sometimes called a stationary wave, it's what happens when you get two identical waves.
Identical how?
Same frequency, same amplitude, and they're traveling in opposite directions, right, in the same medium. And they sort of superimpose, they add up.
Okay.
And the result is, well, it's a wave pattern that oscillates in time, yeah, but its overall shape doesn't actually move through space. It looks like it's standing still, just vibrating.
So it's not actually going anywhere. Like a wave on the ocean goes somewhere, but this doesn't.
Exactly, it just vibrates in place. That's a really key distinction from a traveling wave. Yeah, unlike a traveling wave, which carries energy from point A to point B, a standing wave. Well, the energy is sort of stored in the oscillation, but there's no net movement of energy along its length. It's like its shape is fixed, frozen in space almost, but the points on it are just moving up and down.
And if it has this fixed shape, it must have like specific points that define that shape.
Yeah.
Key features.
It absolutely does. You get these points called nodes and antinodes.
Nodes. Okay, what are they?
Nodes are the points where there's zero movement. Like, absolutely none. The amplitude is permanently zero there.
When?
Because that's where the two waves traveling in opposite directions always meet perfectly out of phase. They completely cancel each other out through destructive interference. Always.
Well, and they're fixed points.
Yep, completely stationary. And the distance between one node and the next one is always exactly half a wavelength of the original traveling waves.
Okay, so nodes are 0 points. What about antinodes? The opposite.
Exactly the opposite. Antinodes are the points right in the middle, between the nodes, where you get the maximum possible oscillation, maximum amplitude.
Because the waves add up there.
Precisely. That's where you get total constructive interference. And just like nodes, adjacent antinodes are also half a wavelength apart.
Now, you mentioned earlier, and this feels important, that these only form under specific conditions. I can't just wave my hand and make one appear.
No, not quite. That's spot on.
Yeah.
They need confinement. They only form when a wave is trapped, basically, within a medium of a fixed length or within certain boundaries.
Okay, like a guitar string. You mentioned that before.
Perfect example. A guitar string is fixed at both ends, right? Those ends have to be nodes. They can't move.
Right.
So that physical constraint means only certain wavelengths can fit perfectly onto that string to form a stable standing wave.
So not just any wave will do.
Nope. Only specific discrete frequencies work. We call these the resonant frequencies or harmonics or sometimes normal modes.
Like playing different notes on the guitar. Each note is a different standing wave pattern.
You got it. The lowest frequency that works is the fundamental, or the first harmonic. That's the simplest pattern. Nodes at the ends, one big antinode in the middle. The string length is exactly half a wavelength then.
Okay.
Higher harmonics, the second, third, and so on. They just fit more half wavelengths onto that same string. L equals lambda, L equals 32 lambda, etc.
So the string length has to be a whole number of half wavelengths.
Pretty much, yeah. This idea of quantization, that only specific discrete values are allowed, it just pops out naturally from confining the wave.
So it really boils down to boundaries and resonance, doesn't it?
Yeah.
The wave hits a boundary, reflects back, and interferes with itself. If the frequency is just right, it resonates and builds up this standing pattern. Is that the secret sauce?
That is the secret sauce. The wave reflecting from a boundary and interfering with the incoming waves is crucial. And the type of boundary fixed, like a guitar string end, or maybe free, determines how it reflects, which affects where the nodes and antinodes end up.
And resonance explains why they get big.
Exactly. Resonance is key. Any system that can oscillate, has natural frequencies it likes to vibrate at. If you drive the system at one of those frequencies, it absorbs energy super efficiently, and the amplitude gets really large. That's what happens with standing waves. The reflections constructively interfere, building up that stable, large amplitude pattern.
And this isn't just for strings, right? You mentioned sound waves, like in a flute.
Absolutely. Same physics, different wave type. Inside a flute or an organ pipe, you have an air column. Sound waves, which are longitudinal pressure waves, travel down the tube.
Okay.
They hit the end, either open or closed, and reflect back. That reflection happens because of a change in what's called acoustic impedance, basically how hard it is for the sound to keep going.
And the reflection interferes.
Yep. Interference between the original and reflected sound waves creates standing wave patterns inside the pipe, with points of high pressure variation, antinodes, and points of no pressure variation, nodes.
It's pretty amazing how these core ideas, confinement, reflection, resonance, leading to standing waves, how they pop up everywhere, from a simple string to a musical instrument.
It really is.
And this understanding that a standing wave is really a system thing, right? It's about the wave interacting with its environment, its boundaries.
Yeah.
That feels like our critical tool for today.
Definitely. Without those specific conditions, you just have traveling waves moving energy around.
Okay, foundation laid. Let's take a giant leap now
Yeah.
to the scale of the entire Earth. You said standing waves the size of the Earth. What physical system are we even talking about there? That sounds huge.
It is huge. The system is called the Earth-Ionosphere cavity. It's basically a natural spherical waveguide.
A waveguide,
Right.
like a giant hollow ball.
Sort of, yeah. You've got the picture. The walls of this waveguide are the Earth's surface, which is a decent electrical conductor.
Okay.
And the lower layers of the ionosphere, maybe 75 to 100 kilometers up, which also acts as a conductor.
And what's in between?
The atmosphere, which acts as an insulator, or what physicists call a dielectric. So you have two conductive surfaces with an insulator sandwiched between them, wrapped around the whole planet.
Okay, so it's like a natural container for waves.
Exactly. Just like a metal box traps microwaves or a pipe guides sound, this cavity acts as a natural resonant cavity for electromagnetic waves. Specifically, extremely low frequency waves, ELF waves.
Why ELF?
Because they have incredibly long wavelengths that are comparable to the size of the Earth itself. So they can travel all the way around the globe inside this cavity without losing much energy, without much attenuation.
Wow. And these are what we call Schumann resonances.
Precisely. Named after Winfried Otto Schumann, who predicted them mathematically back in 1952. They weren't actually measured, confirmed experimentally, until the early 1960s.
And they are. Well, what exactly? Like the Earth's heartbeat.
That's a nice way to put it. They are specific, distinct peaks in the ELF part of the Earth's electromagnetic spectrum. They are the natural resonant frequencies, the notes that this global cavity likes to ring at.
So we really are talking about a wave the size of the Earth. That's mind-blowing. What frequency are we talking? Super low, I guess.
Very low. Theoretically, for a perfect spherical cavity that size, the fundamental frequency should be around 10.6 hertz.
What?
But the observed fundamental is actually lower, closer to 7.83 hertz.
Why the difference?
It's mainly because the ionosphere isn't a perfect conductor, and there are some energy losses. It's not a perfectly sealed box.
Makes sense. Are there other frequencies too? Like harmonics on the guitar string?
Yes, exactly like harmonics. There are higher modes observed around 14.3 hertz, 20.8 hertz, 27.3 hertz, and so on. They do fluctuate a little bit, though, depending on things like solar activity affecting the ionosphere.
Okay, so if the Earth is ringing like this giant low-frequency bell, what's hitting it? What powers these resonances? Where does the energy come from?
That's maybe the most amazing part. Lightning. Global lightning activity.
Lightning, really?
Yeah, think about it. There are thousands of thunderstorms happening all over the planet at any given moment. That means dozens of lightning strikes every second. Wow.
Each lightning strike acts like a huge natural antenna. It radiates a really powerful pulse of electromagnetic energy across a very broad range of frequencies.
So all that lightning energy gets pumped into the cavity.
Right. And what happens is the frequency components of that lightning energy that happen to match the cavity's natural resonant frequencies, the 7.83 hertz, 14.3 hertz, etc., those get amplified. They resonate.
And the other frequencies.
They just die out pretty quickly.
Yeah.
But the resonant ones, they travel around the globe. They reflect off the Earth and the ionosphere. They interfere with them.
Build up stable planet-size standing wave patterns.
You nailed it. The whole Earth-Ionosphere system effectively rings continuously, excited by the constant drumbeat of global lightning.
I love that image. The Earth as a cosmic drum. Now, what kind of wave are we talking about here? Is it like a pressure wave in the air? Is it traveling through the solid Earth?
No, and this is super important for our analogy later. These are classical transverse electromagnetic waves.
Meaning they're like light or radio waves, oscillations of electric and magnetic fields. Transverse means the oscillations are perpendicular to the direction the wave is traveling. And critically, they propagate through the atmosphere, through the near vacuum of the cavity.
So not through the ground.
Definitely not. They are not pressure waves like sound, and they're not waves of electrical current traveling through the solid Earth itself. The Earth is just the lower boundary of the cavity.
How do we even detect these then? They must be faint.
They are very faint, yeah. You need sensitive instruments, specialized antennas, often large vertical ones, or big induction coils to pick up the weak magnetic field component.
Okay, this is a perfect large-scale example of our standing wave principles, isn't it?
Yeah.
You've got the wave, EM, the confinement, Earth-Ionosphere cavity, the reflection, the resonance.
Exactly.
But the key thing is the scale size of the Earth refers to the wavelength fitting the cavity. And the Earth itself is a boundary, not the medium the wave travels through.
That's a crucial distinction, yes.
All right, okay, let's pivot completely. From the megascale down to the micro. Way down, to the electron. The analogy says electrons are standing waves of their own size. This smells like quantum mechanics.
We are definitely diving into quantum mechanics now, yes. The whole idea that particles like electrons could behave like waves, well, that started with Louis de Broglie back in 1924.
The wave-particle duality thing.
Pretty much, yeah. He proposed that all matter, not just light, has wave-like properties. His famous equation, lambda equals h over p, links a particle's wavelength, lambda, to its momentum, p.
But we don't see, like, baseballs acting like waves.
Right, because for everyday objects, the momentum is so large that the wavelength is astronomically small, totally undetectable. But for something tiny and light, like an electron, the wavelength becomes significant, comparable to the size of atoms.
And people proved this, that electrons can be waves.
Oh yes, big time. Experiments in 1927, like those by Davison and Germer, showed electrons diffracting when they pass through a crystal lattice. Diffraction is a classic wave behavior. That was huge confirmation.
Okay, so electrons are waves somehow. How does that connect to standing waves in atoms? You mentioned the Bohr model earlier.
Right. Bohr's model had electrons in specific orbits with specific energies, but he couldn't really explain why only those orbits were allowed. De Broglie offered a reason.
Which was?
He pictured the electron in an atom not as a tiny ball orbiting, but as a circular standing wave wrapped around the nucleus.
A standing wave, like our guitar string again.
Exactly like the guitar string. For the wave to be stable, for it to constructively interfere with itself as it goes around, a whole number of its wavelengths had to fit perfectly into the circumference of the orbit.
Ah, so n times lambda equals 2pr.
You got it. Any orbit where the wavelength didn't fit perfectly would lead to destructive interference, and the wave would cancel itself out. It couldn't exist stably.
So only certain orbits, certain standing wave patterns are allowed. Quantization again.
Quantization falls right out of the wave picture. It's a natural consequence of confining the electron wave to the region around the nucleus.
Okay, but de Broglie's model was still a bit simplistic, wasn't it? Then came Schrödinger.
Right. Erwin Schrödinger, in 1926, developed a much more complete wave theory for matter, the Schrödinger equation. It's like the EFMA of quantum mechanics for how these matter waves behave.
And when you solve that equation for an electron bound to an atom,
The solutions you get are the wave functions, usually written as psi. And for the stable bound states of the electron, these wave functions turn out to be three-dimensional standing waves. Their mathematical form describes a pattern that doesn't change its shape over time, just oscillates.
and just like the guitar string needed fixed ends, the Schrödinger equation needs boundary conditions, right? That limits the solution.
Exactly. You need physically realistic solutions.
Yeah.
The wave function has to be, continuous, finite everywhere, and it has to go to zero, far away from the nucleus. These conditions act just like the fixed ends of the string.
So they drastically limit the possibilities.
Severely. Only a specific, discrete set of wave functions satisfy both the equation and the boundary conditions. These are the atomic orbitals, the s, p, d, f orbitals you learn about in chemistry. Each one corresponds to a specific, allowed, quantized energy level for the electron. Quantization is baked right into the wave mechanics.
Okay, here's where my brain starts to melt a bit. This electron wave, It's not like a water wave or a sound wave or even the Schumann EM wave. What is it a wave of?
Yeah, this is the really non-intuitive quantum leap, you could say. The wave function psi itself isn't a wave of anything physical you can point to. It's actually an abstract mathematical thing. It can even be a complex number.
So, what good is it? What does it tell us?
Its physical meaning comes from work by Max Born. He proposed that the square of the absolute value of the wave function, a 2, at any point in space, tells you the probability density of finding the electron at that point if you were to measure its position.
Probability density. So, not where the electron is, but where it's likely to be.
Exactly. So an atomic orbital, that standing wave pattern, isn't the electron spread out like butter on toast. It's a 3D map of probability.
Right.
It's a cloud showing where you have a higher or lower chance of detecting the electron.
The electron doesn't have a definite position until you look.
That's the standard interpretation, yeah. It exists in this delocalized state, described by the standing wave of probability. So when we talk about the size of the electron standing wave, we mean the spatial extent of this probability cloud, which is determined by the electric field of the nucleus. It's fundamentally different from a physical wavelength in meters, like for the Schumann resonance.
Wow, okay. So a wave of probability. That's profoundly different, governed by totally different roles. Okay, this brings us finally to the trickiest part of the analogy, Tesla waves. You mentioned this term as problematic.
Yeah, problematic is a good word. It's really contentious because people use it to mean different things and often conflate Nikola Tesla's actual historical work and ambitions with much more modern, often pretty speculative theories.
Okay, so let's separate those. First, what was Tesla actually trying to do? His historical vision for wireless power.
His grand dream was the world wireless system.
Right.
He wasn't just thinking about sending signals like radio. He wanted to transmit substantial amounts of electrical power around the globe without wires.
And the Tesla coil was key to that.
Absolutely. He invented it around 1891. It's a resonant transformer circuit that produces very high voltage, high frequency alternating current. That was the engine for his wireless ideas.
And Wardenclyffe Tower on Long Island was his big attempt to build this world system transmitter.
That was the plan, yeah. Started around 1901. The idea was to use this giant Tesla coil to pump electrical charge between the Earth itself and a large elevated terminal, creating electrical oscillations at a specific resonant frequency.
And receiving stations would tune in.
Right. Other stations, also tuned to that exact frequency, could then draw power from this global electrical disturbance. Unfortunately, his funding dried up, and Wardenclyffe was never completed or fully tested.
How did he see this as different from the radio waves Hertz had demonstrated? He wasn't a fan of Hertzian waves, was he?
No, he was quite critical of them for power transmission. He saw conventional radio waves, Hertzian waves, as radiating energy out into space in all directions, which he thought was incredibly wasteful, diminishing rapidly with distance.
So what was his alternative?
He believed the Earth itself could be used as the conductor. He described the Earth as a smooth, perfectly conducting ball. His idea was to transmit energy through the Earth's body using electrical conduction, not radiation through the atmosphere.
Through the ground, literally.
That seems to be what he envisioned, yes. He wanted to make the whole planet resonate electrically.
And he claimed to have detected stationary waves related to this.
He did. While working in Colorado Springs in 1899, he conducted large-scale experiments and reported observing electromagnetic effects from distant lightning storms. He interpreted these effects as stationary waves, standing waves, set up within the Earth. This observation seems to have deeply convinced him that the Earth was a resonant body and that he could artificially excite it to create a global standing wave of electrical current for power transmission.
Okay, so that's historical Tesla. Global power through the Earth, using resonance and conduction. But then there's this other meaning of Tesla waves that you hear about, often in, let's say, less mainstream circles.
Exactly. There's a whole separate body of literature, mostly outside academic physics, that equates the Tesla waves as something fundamentally different, hypothetical scalar waves, or sometimes longitudinal waves in the vacuum.
Scalar waves, longitudinal waves, what are they supposed to be?
Well, the claims are pretty extraordinary. They're often described as being non-electromagnetic, potentially propagating faster than light, operating sort of outside normal space and time constraints, being undetectable by standard EM equipment, and transmitting energy with zero loss.
Wow, that sounds revolutionary if true.
Yeah. Some sources even link these supposed waves to things like consciousness, subtle energy, alternative medicine, going way beyond physics or engineering.
Okay, so what does mainstream physics say about these scalar waves? Do Maxwell's equations allow for them?
Not really, no. According to Maxwell's equations, which are the bedrock of classical electromagnetism and have been confirmed countless times, electromagnetic waves in free space, like a vacuum, are purely transverse. The electric and magnetic fields oscillate perpendicular to the direction the wave travels.
So no longitudinal EM waves, like sound waves.
Yeah. Longitudinal EM waves are only theoretical possibilities under very exotic, unobserved conditions. Like if the photon had a tiny bit of mass, which experiments strongly suggest it doesn't. Now, a scalar wave is a thing in standard physics. It's a wave of a scalar quantity, like pressure in a sound wave or temperature variations. Sound waves are longitudinal, but they need a physical medium, and they are definitely not electromagnetic.
So the speculative Tesla scalar wave idea,
Mm-hmm.
what's the scientific critique? Why isn't it accepted?
Well, several major reasons. First, it generally lacks a rigorous, consistent mathematical framework that fits with the rest of physics. Often, the proponents redefine terms or make claims that seem to violate fundamental principles like conservation of energy.
And the definitions can be a bit slippery.
Often very vague, yes, but the biggest issue is the evidence, or rather, the lack of it.
No proof.
There is simply no credible, reproducible, experimental evidence that validates the existence of these specific kinds of scalar or longitudinal EM waves with the properties claimed. Experiments that have claimed to detect them invariably suffer from significant methodological flaws, poor controls, inability to rule out conventional explanations, inconsistent results. Crucially, they have not been successfully replicated by independent researchers in the wider scientific community.
Right, so that's critical. Okay, this is really interesting then. The term Tesla waves is genuinely confusing because it can mean Tesla's historical idea of conduction through the Earth, or this modern, scientifically unsupported idea of scalar waves. Two totally different concepts hiding under one name.
Exactly. It's crucial to separate them.
So let's bring it all back to the original analogy. Tesla waves are standing waves the size of the Earth, like electrons are standing waves of their own size. We've looked at electrons, we've looked at Schumann resonances, the actual standing wave size of Earth, and we've looked at Tesla's ideas. Can we lay them out side by side now? Use our framework.
Absolutely. Let's do a direct comparison. It really highlights the differences.
Okay, first, the electron wave function, atomic orbital.
Right. Physical system, the atom, nucleus plus electron, scale, angstroms, 10 meters tiny, governing theory, quantum mechanics, Schrödinger equation, nature of wave, 3D standing wave of probability, amplitude, psi, medium, the abstract potential field of the nucleus, scientific status, cornerstone of modern physics, completely verified.
Next, Schumann resonance, global EM wave.
Physical system, the Earth-Ionosphere cavity, that spherical waveguide, scale, megameters, 107 meters, huge, wavelength is Earth's circumference, governing theory, classical electromagnetism, Maxwell's equations, nature of wave, classical transverse electromagnetic TM wave, oscillating E and B fields, medium, the atmosphere near vacuum within the cavity, scientific status, well-documented, measured geophysical fact.
And finally, Tesla's terrestrial transmission is historical concept.
Physical system. He proposed the entire globe as the conductor. Scale. Global planetary distances. Governing theory. His proposed application of classical EM focused on resonance and conduction. Nature of wave. A hypothesized standing wave of electrical current or charge moving through the conductor. Medium. The actual solid and liquid body of the Earth. Scientific status. Historical technological proposal. Visionary but never fully realized or globally verified.
Wow. Okay, laid out like that. The only thing they really seem to share is that very general idea of a standing wave pattern arising from resonance within some kind of confined system.
That's pretty much it. That core metaphor holds.
For the electron, it's the wave's nature plus nuclear confinement. For Schumann, it's EM waves confined in the Earth-Ionosphere cavity. For Tesla's concept, it was the Earth itself hypothesized as a resonant conductor. That basic idea is there in all three.
Yes, the concept of confinement leading to resonant modes is common.
But, and this feels like the crucial point, is that where the valid comparison completely ends.
Absolutely. The divergences are fundamental. They're not just differences in scale, they're differences in kind.
Like, first off, the nature of the wave itself.
Totally different. Electron. An abstract wave of probability. Schumann. A tangible oscillation of real electromagnetic fields. Tesla's proposal. A flow of actual charged particles, electrons, as current through matter. Equating these is scientifically a category error. They aren't the same type of thing at all.
And the governing physics and scale, just worlds apart.
completely incompatible. Quantum mechanics versus classical electromagnetism, angstroms versus megameters, that's 17 orders of magnitude. You can't just map one onto the other. They operate under different fundamental laws.
Then there's the medium versus cavity point you stressed earlier.
Yes, the electron's medium is an abstract potential field. The Schumann waves exist in the cavity between Earth and ionosphere, not through the Earth's bulk. But Tesla's whole idea was explicitly about using the solid and liquid body of the Earth itself as the medium for conduction. That's a huge difference.
And finally, their scientific status and interpretation.
Big difference there, too. Electron wave functions and Schumann resonances are established science, backed by mountains of evidence. Tesla's global power system was a brilliant but ultimately unrealized, unproven technological concept on that scale. And if Tesla waves is meant to refer to modern scalar waves, well, as we said, that lacks any credible scientific basis or evidence.
Okay, so putting it all together, what's the final verdict on the analogy? Tesla waves are standing waves the size of the Earth, like electrons are standing waves of their own size.
The verdict has to be that it's scientifically untenable. It sounds cool, it connects scales, but it fundamentally conflates three radically different phenomena.
It mixes up a quantum probability wave, a classical EM field resonance in a cavity, and a historical engineering proposal for terrestrial conduction.
Precisely. It mashes them together in a way that obscures the crucial distinctions.
What about Tesla detecting stationary waves? Was that likely just Schumann resonances?
That's the most plausible scientific interpretation, yes. It seems highly likely that Tesla, with his sensitive equipment and genius intuition, was among the first to experimentally detect the Earth's natural Schumann resonances caused by lightning. That does show his brilliance in recognizing the Earth could resonate.
But crucially, the phenomenon he observed, EM waves in the cavity, was different from the method he proposed for power transmission, conduction through Earth. The analogy wrongly equates the two.
Exactly. It confuses a natural phenomenon with his specific technological application idea. And, of course, if Tesla waves in the analogy is supposed to mean the modern scalar wave stuff, then the analogy fails completely because those waves haven't been shown to exist.
Right. So at the end of the day, the comparison just doesn't hold water under close scientific scrutiny. An electron's wave function, the Schumann resonance, and Tesla's conduction concept, they are three different things, operating under different physics, at different scales, in different ways. So we started with this really intriguing idea, didn't we? Connecting the tiny and the vast. But the deep dive really shows how vital it is to be precise with our terms and concepts. While that core metaphor of standing waves and resonance is powerful and does apply broadly, the actual physical nature of these waves we looked at is profoundly fundamentally different in each case.
It really is. It's a great reminder that science often finds beautiful, unifying principles like resonance, but we always have to be super careful not to mistake a compelling analogy, however neat it sounds, for an actual scientific equivalence. You have to look at the underlying mechanics.
Makes you wonder, doesn't it? What other common metaphors, maybe in science, maybe even just in everyday life, might lead us down the wrong path if we don't stop and really dig into the fundamental distinctions? What's the main thing sticking in your mind from this that you'll be thinking about later?